Okay, so we will continue with the discussion on gas radiation. In the last few classes we have been deriving the equation of transfer, or also called the RTE, radiative transfer equation. Then we started looking at analytical solutions to the equation of transfer for some simple cases, that is for a grey gas and which is optically thin. Then we started looking at the analytical solution in yesterday's class, and then we came across a very interesting concept called the mean beam length. The mean beam length is a concept wherein we are looking at the average distance travelled by the rays when passing through this participating gas before arriving at a particular area dA. Okay. So in the first part of today's lecture we will elaborate on this concept of mean beam length. We will try to figure out what this exactly means, and then for a general case how do you get the mean beam length, because the mean beam length, as you will see shortly in today's class, will be the starting point for your analysis of radiative heat transfer in enclosures which contain a absorbing and emitting gas. Okay. In the previous weeks we looked at radiation heat transfer from an evacuated enclosure or an enclosure containing air which is radiatively transparent or radiatively non-participating. Okay. Now let us consider a hemispherical gas volume. Consider a hemispherical gas volume. The radius is given, the radius of the hemisphere is given by r. There is a elemental area dA at the center of this, at the center of the bottom surface of the hemisphere. Okay. We are looking at this gas volume which is absorbing and emitting. I am looking at a small area on the top of this hemisphere, and then we are connecting this area to this area, that is we are trying to find out what is the radiation from here which is arriving here, that is radiation originating from this and then travelling through the gas volume. Okay. Now the gas is at a temperature Tg, it is an optically thin gas. Okay. These are the two assumptions, and this is hemispherical gas volume. The idea behind this exercise is to understand more about the concept of mean beam length. Okay. Now in yesterday's class we derived that for the optically thin gas, okay, for radiation from somewhere from a surface arriving at a length L, the expression for the intensity at I plus of L, where I plus is the positive direction of x, is given by this. Have I made any mistake? Is it fine? Okay. Now what I am saying is, instead of I plus, from I plus L we can calculate the Q also. Instead of I plus I am taking Q minus, because Q minus is arriving at this. Okay. I am considering R to be positive in this direction, it is minus. So I am saying Q minus R will be pi times this intensity. So I have just used this intensity expression, I multiplied by pi because it is isotropic. I also done one more thing, instead of L I have used R. Okay. There is no problem with this. Now it is possible for me to cancel the pi, right. One more thing what I am going to do is Tw by Tg Tw by Tg is much less than 1. Okay. It is a gas which is contributing more to the radiation. Tw may be at 300 Kelvin, the gas may be at 1500 Kelvin, it may be hot combustion gases, the walls are not very hot. Then what can happen to the first term? You can knock it off. Okay. So this will now become okay. Now for an optically thin gas, kappa r is much small compared to, quite small compared to 1. Therefore 1 minus e to the power of minus kappa r can be expanded as kr, simply kr. 1 minus e to the power of minus 0.01 is just 0.01, correct. Okay. So this can be written as sigma Tg to the power of 4 into kr. Okay. Therefore if I am able to write a flux as sigma Tg to the power of 4 multiplied by some k into r, whatever is within the brackets can be called as an equivalent emissivity, correct. Is that okay? Therefore, please note that, please look at the assumptions under which this analysis is valid. Okay. Now, this is just to, therefore, epsilon g so this is the thermal part. So, when we considered a plane wall which was black, which was at a temperature Tw surrounded by an isothermal gas at Tg, we figured out that the mean beam length was equal to 2L. Here the mean beam length equal to, very good. So, mean beam length is equal to R. So, for a plain gas layer of thickness L, the mean beam length is 2L. For a hemispherical gas volume, the mean beam length is R. However, these types of analytical ways or analytical ways of deriving this mean beam length cannot be done for geometry after geometry. Certain mean beam lengths have to be calculated or evaluated. Therefore, what is the next logical step? I will give you a table which can be used, which you can use in the exams or while solving problems where mean beam length for various things is given. In that, the hemispherical gas volume and the parallel plate will also be there, but instead of 2L it may be 1.8L. There is a small difference. Instead of 2L it is 1.8L because of the expansion of E3 of T in the vicinity of T equal to 0. There may be a small, because it is not exactly equal to half. Okay. So, now for an arbitrary shape, if it is not a volume, for an arbitrary shape, what is the mean beam length? Okay. Mean beam length is 3.6 times V by A. If you apply the 3.6 V by A for the plain gas layer of thickness L, what will you get? 1.8L. That is why I said it will not be 2L, it will be 1.8L. This comes from calculations and evaluate the exponential integral and get it. Okay. Now I will give you the, this contains additional information also which will be used for solving problems the lectures I am going to deliver next week. I asked somebody to take 55 copies, they put that, and with that they have taken the Xerox. Sampath, yeah, you take it and, yeah, now we are looking only at the first sheet. Oh, you have a problem. There are four sides to this. Okay, please look at this. Mean beam length for radiation from the entire gas volume in common geometries. Mudit, you got it? You have problem? What's happening? Yeah, you can keep that. There should be 4 sides. Alok. Srikanth, you got it? Rohit, you have any spare copies? You want, is it? Yeah. There are 4 sites, do not bother about sites 2, 3, 4. They are emissivities of carbon dioxide and water vapor, which we will use in the next week's classes. Okay. So, the mean beam length for various geometry, serial number, geometry. So, sphere of diameter d radiating to inside surface 0.65 d, hemisphere 0.5 d, correct? We worked at the hemisphere today's class, it is r, it is 0.5 d. Then between 2 parallel plates, look at point number 7, serial number 7, it is 1.8 L, okay. So, arbitrary shape 3.6 V by A. So, with mean beam length you can proceed, right. One. Now, we will solve some problems. Problem number 30, 36, 37, problem number 37. Problem number 37, consider a grey gas with an absorption coefficient of, consider a grey gas with an absorption coefficient of kappa equal to 0.15 meter inverse. Consider a grey gas with an absorption coefficient of kappa equal to 0.15 meter inverse, that is 1 by meter. It is maintained at a temperature of 400 Kelvin. Consider a grey gas kappa equal to 0.15 Tw equal to 400 Kelvin and it is maintained at a temperature of 400 Kelvin and is 0.4 meters thick, 40 centimeters thick. Huh?
Tg for
sorry, it is maintained at a temperature of 400 Kelvin and is 0.4 meter thick. The gas layer is 0.4 meter thick, no problem, right, and is 0.4 meters thick, sorry it is not the wall. A black wall at 500 Kelvin is at x equal to 0, a black wall at 500 Kelvin is at x equal to 0, okay. Sorry if I have confused you. Tw is 500 Kelvin, Tg equal to 400 Kelvin, thickness L equal to 40 centimeter, kappa equal to 0.515 meter inverse, everything is fine, data is fine. Determine the intensity at x equal to 0.4 meter for, determine the intensity at x equal to 0.4 meter for A, determine the intensity at x equal to 0 for A straight path, determine the intensity for A or that is 1, first part of the question, determine the intensity for A straight path, B slant path at 60 degrees, determine the intensity at x equal to 0.4 meter for a straight path, or if you feel it is confusing I can reword it as determine the intensity at x equal to 0.4 meter for a straight path as well as for a slant path at 60 degrees, full stop. Use that small t approximation, use the small t approximation, use the small t approximation as well as the exponential integral, use the small t approximation as well as the exponential integral for evaluating the heat flux at x equal to 0.4 meters. Use the small t approximation as well as the exponential integral for evaluating the heat flux at x equal to 0.4 meter and comment on the results. use the small t approximation as well as the exponential integral for evaluating the heat flux at x equal to 0.4 and comment on the results. So you do not require the mean beam length for this, right? Okay, you can do because analytical formula we have. Pranay, anybody else who came late? Who is without the? You have? Huh? What is it? Sphere. I didn't give sphere now.
Here. If we substitute in 3.6 V by A, it will come 0.60.
No, that small differences will be there. But this 3.6 V by A, do not try to check whether that formula is correct. This is the general formula which is approximate. See, mean beam length is approximately, if you do not know anything, use this. For sphere and other things, we can exactly calculate that 0.65 is accurate. Okay. Yeah. This is just a test of how you have understood the exact solution well, that is all, simple and straightforward. I am asking you to solve in two ways. Use the small t approximation where E3 of t equal to half minus t, that is first part. The second part, you do not use this, directly use E3 from the tables, okay. Should take less than 10 minutes. It was 38, problem number 38 or 37. Correct. So, there is a schematic of the geometry under consideration. Now we can straight away start getting the solution for theta equal to 0, I plus L sigma e to the power of minus k L (1076.1). Fine. Now what is Vinay, is it okay? What is I naught at what is I naught plus? I naught plus. How much is it? What is the intensity coming out of the black wall? 1 point. Okay. Okay, this is not asked in the question, but I am trying to use this to get some more insight into the problem, right? This is not asked. You have got this first part. Now I am asking you to look at the ratio of, please look at the board, I at L divided by I at 0. The IL at divided by I at 0 is almost equal to 0.98 or something, is 98 or 99%. Therefore, the gas is not absorbing much. Therefore, it is an optically thin gas. Okay, this is the sort of insight you have to get. Just blindly you can substitute the formula and get the result. But now if you do this, now if I naught at if I at L divided by I naught is 0.5 or 0.6, then it is a very questionable assumption. But we have not made any assumption so far. The optically thin gas assumption will come okay when you are using that in the Q. Yes, correct. This is okay, right. Now what is the second part? You have to do it for please look at the units, watts per meter square per steradian. Okay. Fine. So this answers the first part of the question. What is the intensity? What is the intensity at x equal to 0.4 meter for the two paths, straight path and the slant path? Now coming to the third part of the question, what is the QL? Small t approximation. What is small t approximation? E3 of x equal to half minus t, okay, where now how much is it? 0.06. Correct, that is my small t. Now if I do the, now I will do it here. Is it correct? Plus 400. Is this correct? Yeah. So what do you get now? 2623. Did I make any mistake? Where is the factor of 2? Let us see. Let us see. What is the final solution? Sigma sigma Tg to the power of 4 0.88 This one also? Ah. Did I do that? No. Tg is what? Is it correct now? Huh? What is the answer? Watts per? Very good. So this is QL small t. Now QL EI. This is okay? Plus into this is correct? 2 bothers us throughout. 2 sigma TW E3. Okay. Now what is the E3 of 0.5? E3 of 0.06? 44? Correct. Now we can use this QL. What was TG? 400. What is this? Point? less than 1%. Yeah, so good man. Point, how much error? 0.84%, very good, simple. So what can you infer from this? If tau is equal to 0.05, 0.06, if it is less than around 0.1, then this optically thin gas is a good assumption. Okay. So whether it is optically thin or thick not only depends on the absorptivity, it also depends on the length. So it is the product which matters. It can be a very heavily absorbing gas, but it is only 1 millimeter or 2 millimeters, it does not matter. It can be a poorly absorbing gas, but if you are taking a large thickness L, K into L will be the trouble, will create the trouble. Okay. However, if you are treating it as an insulation or something, or you want this radiation to be attenuated, it is good for us, correct. But if you want, if you don't want the gas to create a lot of mischief, then you don't want it to be very optically thick gas, correct. But these are all we have made so many assumptions. It is a grey gas, it is only one gas. It is a grey gas, it is only one gas, it is isothermal. Many of these assumptions can be questioned. Most importantly, this analysis cannot be used in an IC engine or a furnace simply because there is no one gas. So the next level of complexity will be how to get the epsilon g for a mixture of gases. What will happen if the walls are not black? So we will go up to a certain level and stop. Beyond that it is research. So we will now look at a modified enclosure theory when the walls are not black, but still it is optically thin, it is still a single gas, one gas, it is grey. Then are there some recipes available if there is a mixture of gases? Yes, carbon dioxide and water vapor, because they are used, they keep coming in power plants, that is right, in power plants, IC engines and all that. CO2 and H2O, people have done experiments and at 1 atmosphere pressure, and they have given the charts, which incidentally are given in pages 2, 3, 4 of the handout. So there is a recipe available. We'll look at the recipe in the next class, and then using that you can calculate. Okay, but beyond that, if it is other pressures or other things, we'll have to solve the spectral radiative transfer equation and get all this. But this is not the end of the story. This is still an absorbing and emitting gas only. If it is a mixture of gases, it is absorbing, emitting and scattering anisotropically. It is really difficult. Okay. Are you able to appreciate the complexities involved? We will do now, next we will do one more problem where there are two parallel plates. Okay. Suppose there is a black wall, okay. There is a gas layer, the gas layer is having a temperature which is different from the black wall. We figured out how to solve the problem, okay. Right side I put one more wall which is parallel to this, that is a parallel plate formula, but between the two parallel plates I am putting a gas which creates mischief. It is not vacuum, but I am saying it is optically thin. How will you figure out the heat flux at the two ends and heat flux at the center of this arrangement? That is what we are going to look at, right. Problem number 38. Two infinitely long vertical plates are parallel to each other. Two infinitely long vertical parallel plates, two infinitely long vertical plates are parallel to each other. full stop. Both the plates are black, and are at temperatures both the plates are black and are at temperatures 1500 and 900 Kelvin respectively, and are at temperatures, okay, to be more clear, T1 equal to 1500 Kelvin and T2 equal to 900 Kelvin respectively. The spacing between the two plates is 1.5 meter. The spacing between the plates is 1.5 meter and is filled with a grey gas. The spacing between the plates is 1.5 meter and is filled with a grey gas at 1200 Kelvin. With an absorption coefficient of 0.08. Is filled with a grey gas at 1200 Kelvin with an absorption coefficient of 0.08 meter inverse. Determine the heat transfer rate at each of the two boundaries. Determine the heat transfer rate at each of the two boundaries. Determine the radiative heat transfer rate. Okay. Determine the radiative heat transfer rate. What else could be there? Conduction is not there. Convection. I didn't tell you whether it's a Boussinesq fluid, natural convection is there, or I didn't say air is something is blown over, there is a fan or a blower. Or, okay. Now it's pretty interesting because from left side also some activity is there, from right side also some activity is there. Superposition can be used. You have to just combine the two solutions. But for left to right, x is in the positive direction, but right to left it is in negative direction. So you have to take the algebraic sum of the heat fluxes. Okay, and the heat flux expression should be asymptotically correct. If the kappa is equal to 0, what is the expression you have to get? Q12 equal to sigma T1 to the power of 4 minus T2 to the power of 4 divided by 1 by epsilon 1 plus 1 by epsilon 2 minus 1. Here epsilon 1 is equal to epsilon 2 is equal to 1. So you will get a simple expression sigma of T1 to the power of 4 minus T2 to the power of 4. So first it is good practice to just draw two parallel plates T1 T2, put a gas layer at Tg, get the general expression for heat flux at the x equal to 0 and x equal to L. Then towards the end just substitute all these values and get the answer. Okay, you can take the general solution Tw to the power of 4 1 minus E3 of tau L, all those expressions you can use. You do not have to start from dI by dx equal to, okay. Yes. What is this? This is x. How much was this? Kappa?
0.08.
Okay, all this is infinitely deep, this infinitely deep. It is infinitely long and infinitely deep. So the best thing would be to take a section x, find out what is the heat flux arriving at station x from the left side, from the right side, algebraic sum is the net radiative heat flux at x. Then put x equal to 0 and x equal to 1.5 meter, you are home. Is it okay? Instead of x, I may use tau of x. that may be better for me, because the E3 is available for in terms of tau. Okay, instead of x I can use tau, right. Now I will say q plus at x coming from left side, correct. What is the expression for this? Sigma T1 to the power of 4 into 2E3, 2
2 sigma T1 power 4 E3.
2 3.
from the left, I am taking from the left. X is from 1 2 sigma E3 of tau of x. Oh, not, it's not over then, plus 1 second. No, T2 will not come now. 2, no 2. Sigma 1 minus okay. Towards the end we will say that it is optically thin gas and then use the small t approximation. Now we will give the general solution. Now what is the Qx? Okay man, 0.1 only, otherwise you stick with this. So let us look at the 2x minus from right side, two sigma, very good, 2 sigma what is that?
L minus
L minus x, yeah, that is the distance. No, that is kappa L minus x, no problem. Is that correct? Plus but what is the direction in which this fellow heat flux is a vector, correct? What is the direction in which this fellow is coming? He is coming from left to right or right to left? Right to left. Therefore, if you want to have the net flux, you have to take q1 qx left minus q, okay. So net flux at okay. Now shall we use a small t approximation? You want to see chart? Okay, yeah, then proceed. So I will do something on the board. Let me take the special case tau of x kappa equal to 0. What is E3 of tau of x? 0.5. Therefore, because the second term this fellow E3 is half into half 1, this fellow gets knocked off. So the contribution from the gas volume term is 0 for both the left and the right, okay. So this is consistent with our understanding of the problem. So therefore whatever the formula which we derived must be correct. We found out now? Yeah, now we can get the values of Qx left and Qx right. Please tell me. Now we have to substitute correct. So we need to get Q at 0 and Q at L. What are you doing now? Is 0 or L? Or you are doing at the center? 0 and L, okay. Because I left it open at X, okay. Is everybody through with the procedure? So it involves more calculations because there are two, you have to look at the E3 twice or maybe 4 times, because I want you to evaluate at x equal to 0 and x equal to L. Just give me one answer, x equal to 0. How many of you are doing x equal to 0? Yeah, we will just finish this and then I will distribute the assignment. So tau of x equal to why 0.12?
0.08 into 1.4.
Oh, the E3 of tau of x is 0.12, okay. E3 no at x equal to 0 equal to 0.5, okay. Therefore into 0, all right. E3 of tau L minus tau x is E3 of tau L minus E3 of tau x, that is correct. Okay, what is this? 0.12 yeah, please complete this. Okay, please complete this. What is the answer?
2.342
kilowatts 10 to the power of 5.